Hello and welcome to this presentation, an animated introduction to vibration analysis. My name is Jason Tranter. I'm the founder and managing director of Mobius Institute. Now, the idea of this presentation is to take a quick look at all the primary vibration analysis techniques: spectra, time waveform analysis, phase analysis, and orbits, as well as high frequency detection techniques called, demodulation, enveloping, and so on. The idea is so that if you're new to vibration analysis, you've got an idea of the types of tools at your fingertips. If you're in a plant where vibration analysis is being performed either by people in the company or consultants, you've got an idea of what sorts of tests are available and what sort of information can be gained, and also get an idea whether they are actually using the right types of tests. Anyway, let's get started. The aim is to avoid that. We don't want the equipment failing catastrophically, which causes secondary damage, which causes downtime, potentially safety incidents. We lose production, we have much higher costs associated with the repair. There are a lot of reasons we want to avoid that. So we can use vibration analysis alongside other technologies to get the earliest warning that that is beginning to occur, that the early stages of failure are occurring, which may end up like that if we don't do anything about it. And vibration analysis is a terrific tool for doing exactly that, because vibration analysis, in a sense, enables us to look inside the machine and see exactly what's going on, whether it's gearbox with bearings, blowers and fans and so on. We want to be able to look at those bearings, look at the gears, look at the impellers and so on, and find out what's going on. If we could look at that bearing and tell that it's lubricated properly, installed properly, there's no damage to the raceways, there's no damage to the rolling elements, then we have the confidence that we can go on producing our product and it's all good. But if we see something, then we can act. Same goes with gears, whether they're timing gears or inside a gearbox. Are they aligned? Are they lubricated? Is there damage to the teeth? Anywhere? Whatever the case may be. Vibration analysis lets us look inside the machine. Now, in this case, we've got, the motor driving a pump and a vibration sensor sitting up on top. Now, I'll explain a bit more about that in just a moment. But you may first imagine that, all the vibration is transmitted along and goes up to this point, and maybe from this side as well. And that's one of the things I'll mention a bit more about in a moment. Just where is the vibration coming from and how's it getting to that sensor? But one of the keys is that vibration analysis, in a sense, enables us to sort of listen. Well, what is happening with the shaft? What's happening with the bearings? What's happening with the rotor bars? Now, we pick up all those sounds from here. They all combine together into one measurement, but separating them in frequency and some of the other things we'll explain let us do that, so we get an idea of the health of each of those components. Over this side, that bearing is not in good condition. For the pump, we've got pump cavitation. On the machine head, okay, not many machines sound like that, but anyway. Okay, so the way we do this is, as you've just seen, we can put the vibration sensor up there on the bearing, and all the vibration is transmitted, through the machine itself up to that point. The sensor has to be mounted properly. That is very important, so that all those high and low frequencies get up into that sensor. But the fact is, when we mount it up on top, that is sensitive to the vertical motion. Whereas if I move it to the horizontal location, that's now much more sensitive to the horizontal motion. So, for example, if it was rocking back and forward due to looseness or resonance, then the horizontal measurement will tell us about that. And whether it's vertical or horizontal, they tell us, those two positions tell us about radial vibration radiating out. So if there was misalignment and offset or parallel misalignment, or unbalance, we get a lot of that sort of up and down and side to side motion. But with angular misalignment, for example, and certain types of bearing faults, it's more sensitive in the axial direction. So we put the sensor in line with the shaft, you might say, sort of in a position like that. And also, all the vibration from here isn't necessarily going to transmit through the coupling. So what we really want to do is try to measure at every single bearing to be absolutely sure we're picking up all the vibration, especially these high frequencies that don't travel very far. And I'll mention a bit more about that later on. Okay, so our sensor is sensing the motion, in this particular case, what I described so far, on the bearing itself. Now imagine if this was the shaft inside the machine, and like a lot of my animations that you'll see today, I exaggerate some of the motion. So there's the shaft moving around in that sort of circular motion, perhaps because of unbalance or a bent shaft. And for simplicity's sake, we've put a dial indicator on the shaft. So as the shaft moves back and forward, it pushes the plunger in and out. We see the needle move, and we get this pattern. That pattern is a sine wave. It's a pure sine wave. It has a single frequency and a single amplitude. Now this isn't the way we normally measure vibration. In certain machines, and I'll talk more about that a little later, we can use these non-contact eddy current probes, also known as proximity probes, and it is literally measuring the distance between the tip and the shaft. We use those in certain applications. We used to use velocity probes a lot, but now it's more common to use accelerometers. It sits on the bearing housing and senses how it is moving in response to all the things going on inside the machine. Either way, if we've only got one force, if you like, one source of vibration, we will see just one frequency and one amplitude. In reality, there are multiple sources of vibration inside the machine, which we'll talk about in just a moment, and therefore we have a more sophisticated or more complicated time waveform. But if I speed the machine up, you see the shaft is now moving, it has more cycles per second or more cycles per minute, and therefore our cycles on our little time waveform graph here are closer together. Alternatively, let's just push the amplitude up. So if I make more movements, my time waveform is going to reflect that. Now the amplitude is greater. Of course, it looks a bit silly there, but anyway, you see the point I'm trying to make. So that's the basic thing. This is one frequency, one signal, one frequency. It's a perfect sine wave. It has a certain frequency and it has a certain amplitude, and that's all very important. Now, let's go to a bit of a closer real-world situation. So what I'm going to do here is I've got a green bearing with a grey shaft and grey pulley, and this orange fan sitting here, the orange blades. So what I'm going to do is turn on the vibration that's coming from that grey shaft. Now, just to clarify something, all the vibration is being measured on this bearing with our accelerometer. That's sort of what we're simulating. But what I can do, just for educational purposes, is turn on and off these three dominant sources of vibration. So there is the vibration at the running speed at the once per revolution frequency. If I speed up the machine, then like we saw just before, the waves get a bit closer together. If I have more amplitude, I get a bigger signal. So from this grey shaft, I've got this grey vibration. That's sort of what we saw a moment ago. I'm going to turn that off, and let's have a look at the green bearing now. And lo and behold, now I've got green vibration, but it's clearly a different frequency. It's a higher frequency. Now, in reality, bearings can generate 4 different frequencies, and those frequencies, those signals, if you like, are not normally simple and sinusoidal. We'll talk more about that soon. For now, let's just focus on the fact that we've got a different frequency because the bearings, as the rolling elements roll around, the interactions that occur are a different frequency from just the running speed. Now, if the bearings were in tip-top condition, very good condition, I actually don't expect to see any green vibration, but as the problem develops, I get more and more green vibration related to the bearings. Let's turn that off for a second. I've got 10 blades on this fan, and if the air flowed through those blades nice and uniformly, I might not get very much vibration. But if there wasn't as much uniformity, if the blades were bent, let's say, or a number of other potential problems, I get more vibration. But this is a different frequency from the two we've seen before. So I've got my green vibration from the bearings, my grey vibration just from the shaft once per revolution vibration, and because I've got 10 blades, which the way I've set this up, it's a higher frequency than the bearing frequency, we can see more of a problem, less of a problem. Now, from everything that I've described, hey, you're a budding vibration analyst now. If you could see what I'm seeing there, and you see that the little grey waveform is low in amplitude, you'd be saying, oh good, the machine's nicely balanced. Oops, it's not as balanced as well. Oop, the bearings are in good condition, the bearings are getting worse and worse. So you get the idea. Unfortunately, this is not exactly how it works. Because we don't see those three nicely coloured signals, we see the summation of all three. They add together, they combine to make the housing of that bearing move according to this red line, and that's what the sensor feels. That's what this accelerometer feels, and that's therefore the signal that goes up to our data collector. So that's what's happening. That's there, but as you can see, could you look at that red waveform and see whether it's balanced or there's a bearing problem? No, it's difficult. So that's why we use spectrum analysis. Spectrum analysis, so there's those three signals again with the red one turned off. There's the three, and I can turn down the bearing and, whatever. What I'm going to do is show you that what we've been looking at all along is actually in 3 dimensions. We've got amplitude, time, and frequency along here. If the machine is running faster, the machine generates higher frequencies, so you see them sort of moving off to the right. If the machine's running slower, there are lower frequencies, it's closer to the left. So this is increasing frequency, and we have separated the 3 sources of vibration in proportion to their frequencies. Low frequency, higher frequency, highest frequency. More amplitude, less amplitude. So, rather than looking at it in that format, what I'm going to do is come and look at it end on. And there you go. That is the vibration spectrum. Imagine there's a grey waveform behind here, a green waveform behind here, and the orange waveform there. I can just sort of simplify it a bit more. The calculation that does this is called the fast Fourier transform. So sometimes you'll hear Fourier analysis, or you'll hear the FFT, the fast Fourier transform. Either way, this is basically what we end up with, and just to keep it simple, I'm just going to line that, oops-a-daisy, just get that lined up. Anyway, the reason I'm trying to do that, and not doing it very well, is that what we've shown here is this is the frequency, and I'm simulating this as if right now, that's what I was just trying to do with the knob, make it vibrate at 30 Hertz, because I've got 10 blades, so therefore the vibration from the fan would be at 300 Hertz. And the better way to say it is, well, this is 1x, 1 times the running speed. I've got 10 blades, so this peak would be 10x. So if someone talks about vibration frequency, you might hear them say, oh, it was the 10x peak. What's a 10x peak? Well, the 10x peak is 10 times the running speed. And a vibration analyst might think, oh, I wonder if there were 10 blades in that fan or 10 vanes in that pump. That's the sort of thing. If you look, and I didn't line it up very well, but this green vibration is never exactly 9x or 10x or 3x. It's always 3 point something, 5 point something, 7 point something. It always works out that way. But the beauty of all this is that there's the vibration from the shaft, there's the vibration from the bearing, and there's the vibration from the fan. So basically I might take a measurement one day, and it, let's just say, looks like this. Whoops, daisy, I turned that too far, didn't I? So it might look like that. No green vibration, a little bit of grey, a little bit of orange. Now, of course, in the vibration world, we would just say that's 1x and 10x. And if I was watching this machine every 30 days, I'm doing tests according to the PF interval. It's understanding the failure modes to say, well, how quickly does the condition degrade? And I've got to make sure that I get at least 2 measurements in the time where it's going from healthy to the time where it is, well, functionally failed, where we are being forced, either because it's catastrophically failed or it's just unable to perform its function. We want to take enough measurements to detect that. It's not so much to do with criticality. Criticality tells us whether we can justify doing it. The PF interval, or the time to failure, it tells us how often we should do tests. But anyway, if I take one measurement and then I come back later and I see 30 days later it's like this, 60 days later it's like this, I can say, okay, the unbalance is growing. And I can decide whether I want to do something about this high level of vibration. Do I think this is going to cause the machine to fail, the structure to fail? Is it creating noise that's creating a quality problem or a noise issue for workers and whatever? But the question I should also be asking myself is this going to do damage to the bearings? Because while we're monitoring the condition of this machine and we've got this unbalance, we damage the bearings. That's one of the root causes of bearing failure, misalignments and unbalance and these sorts of faults. So now we've seen the bearings start to fail. The patterns are a little bit different to this, but you get the principle. So we'd like to know something about the machine, so we know its running speed, something about the bearings, something about the fan. So that's the basic idea of spectrum analysis. It's condition monitoring because we're watching how the condition changes over time, and hopefully we don't see anything because we're running the machine properly and we've got it nicely balanced, lubricated, aligned and all those things. So therefore, normally I would hope to see a real boring spectrum. It might have little peaks around the place, but there will always be a peak at the running speed, 1x. You see, this has been normalized now. It's in orders instead of hertz or CPM, cycles per minute. But if I do have unbalance, the 1x peak goes up. If there's resonance, it amplifies the vibration and we tend to see the base of the peak sort of broaden out. Misalignment, now this is puzzling, misalignment, because if it's angular we see it in the axial direction, mostly at the running speed. If we've got parallel or offset misalignment, we may see 1x go up and or 2x, twice running speed, and or 3x and 4x and 5x. It all depends on the degree of misalignment, the axis where you're measuring, the type of coupling you're using. All those things affect the pattern that you'll actually see. Looseness, imagine the bearing sort of just loose, too much clearance, and there's rattling as a result, then we see harmonics. Harmonics occur when the vibration is not smooth. That nice simple sine wave creates one peak. When there is impacting going on or the vibration is not as smooth, just sort of distorted vibration, hard to summarize very quickly, we will see, instead of just one peak, we'll see 2, 3, 4, 5, and they may all be a similar amplitude. In fact, they might go up in amplitude or they'll go down. And we sometimes see the noise floor, the bottom of the graph, lift up as well. So, lots of different patterns. But one of the keys is not to get locked into trying to remember patterns. Don't be a wall chart analyst that looks at a spectrum and then looks up at the wall chart and says, that spectrum looks like this sort of fault. What you need to do, in my humble opinion, is become one with the machine. Think about your machines. Think about their failure modes. Think about the technologies that will detect those failure modes. Think about how you should take your vibration readings and where you should take your measurements and so on. And if you understand why the vibration changes the way it does, then not only do you make sure that you set up the analyzer to capture that vibration and you take measurements in locations that will capture it, when you see patterns like this or patterns like that or patterns like this for bearings, you won't just think of the wall chart, you'll think, aha, harmonics, what does that tell me? Sidebands, what would that tell me? Lots of peaks, high amplitude, low amplitude, all these patterns should tell you what must be happening inside the machine in order to create those patterns. And that, in my opinion, is how you become a good vibration analyst. Understand the machine, understand where the vibration comes from, understand the analyzer and sort of what you're seeing in the data, and then you can figure out what's going on and not just look at a wall chart and say, that spectrum looks a bit like that one, it must be looseness. That's the trouble. A lot of people get reports and it just says there's looseness, and I think, oh, what does that mean? What do I do? Anyway, another story. So that is basically spectrum analysis. Now there's a special type of spectrum analysis where we, instead of just looking at the normal sort of range of frequencies, let's just simplify it and say, up to 1,000 hertz or something like that. Hertz is cycles per second. Instead we look beyond that, because it turns out that when we have, for example, a fault on the outer race of the bearing, while the rolling elements are not making contact with that point, there is no vibration. But when the rolling elements come along and make contact with the spool or the crack or whatever is sitting there, we get an impact, and you can see these white waves rushing out. That's called stress waves or shock pulses. If you take any two metallic objects and clack them together, you put a little short stress wave through those two items, and we can detect that. Now there's a lot more I could say on this topic, but basically we can detect that because at the very earliest signs of a problem, either inside the bearing or with gears and other sort of metal-to-metal fault conditions like looseness and broken rotor bars, in that earliest stage we may not see any normal vibration. The amplitude is so low, the frequency is so high that we don't see it in our normal measurements. So we need to use a technique that looks for problems like this. So there's a problem on the outer race, problem on the inner race. Notice it's a higher frequency, but we still see those little white pulses, and if there's damage to the rolling elements themselves. So this technique goes by many different names depending on the vendor. It can be called demodulation, enveloping, shock pulse, peak view, spike energy, HFD, C, Swan, and there's probably other names out there. I apologize if I've forgotten the one you're using. But bottom line is they all, in essence, do the same sort of thing. The first thing they do is they filter away all the high amplitude, low frequency vibration, the normal stuff we would expect to see in a spectrum. That is much higher amplitude compared to what we're looking at with these stress waves and so on. So we filter all that away to get rid of it, and then we just focus our attention on the high frequency, low amplitude vibration. And using these techniques we sort of translate that back to the low frequency part of our spectrum where we can do our normal spectrum analysis and look for all those telltale peaks at the key frequencies for bearings and gears and such. Okay, so that's an important technique which you should certainly be using, in my opinion, if you've got rolling element bearings, if you want an early warning. Now, when we started all of this, I showed you a time waveform. We looked and saw it, and I'll show you that again just if you're not sure. The time waveform is more complicated to look at, but the time waveform can reveal all sorts of fault conditions that you might miss otherwise. So here's a time waveform, and I'll get back to what this means, but it's sort of like having a movie camera that's filming inside your machine and seeing every little thing that goes on as those balls roll around inside your bearing, as the teeth mesh together. It's seeing everything from moment to moment to moment. The spectrum takes sort of like a long record of all of that, a whole lot of that film or a whole lot of that recording, and tries to summarize it into a spectrum. And sometimes that summarization process, is that the right word, actually loses information. The time waveform tells us exactly what happened. So we saw earlier, as I clicked on the little buttons, these are the individual components of the time waveform. This red one is the raw time waveform. Simplified, but that's the raw time waveform. So in other words, in order to collect this thing called a time waveform, you don't necessarily have to do anything different. You just have to tell your analyzer to store it. Of course, you also want to look at it. Now, the truth is that to do spectrum analysis correctly, you need to look very carefully at the Fmax, which is the highest frequency in the spectrum, and the resolution. It's sort of like the clarity, the amount of detail in that spectrum. And when you make those settings, that affects the time waveform that needs to be captured to create that spectrum. Well, you need to look at what that time waveform will look like and ensure that what you hope to see in a time waveform will be visible. And that's where a lot of vibration analysts get caught up. They look at the time waveform and they see it just looks boring. It just looks like a whole lot of just blue graph, and they say, it's not telling me anything, I'm not going to bother with this anymore. Please bother. Please just make sure you get the settings right. We spend a lot of time on this in training to make sure people understand why. And what I'm about to show you is sort of a simplified explanation of why people get it wrong and what you need to know. Now, remember I said time waveform analysis is a little bit like using a video camera. And you're probably aware that a video camera records, I think it's 24 frames per second, because when you play those 24 frames a second back, our brains can't tell that it's just 24 pictures that we looked at in that second. It looks like it's all continuous. Well, time waveforms are the same. When we choose the settings for our spectrum, the analyzer decides how frequently it's going to convert that analog voltage from the sensor into a digital number that the analyzer has to use, because it's like a mini computer. And that's what those red dots represent. The red dots represent each time that it converted the analog to digital. It might sound very technical, but it's pretty simple really. And you can see in this case that all those little red dots follow exactly along the black line, which is, let's call it the analog signal, the actual vibration that we're measuring. So that's all very simple, but what if it was a gearbox, or gear, and there was damage on it? Well, we can translate these little red dots onto the surface of the machine we're testing, because if you can imagine, just as the camera takes a whole bunch of shots, it's also like taking little mini pictures at the gear as it's going past. Now, if you watch on the left, you can see the damaged tooth, and on the yellow graph there you can see that there's only really maybe one or two red dots on that spike of vibration. The bottom line is, I don't want to make it too complicated, the bottom line is we would like to have lots of red dots on those teeth, especially on the broken tooth, so that we know what's going on. And that all depends on the settings that you use. It's important to get the settings right. So, I'll show you one example. Imagine here we have a rolling element that is damaged, and that rolling element, rolls up out of the load zone, and now it's going to go down into the load zone. Well, this is what the time waveform shows us. In the load zone is where the amplitude's highest, out of the load zone is where the amplitude's lowest. So that's the load zone, that's sort of taking all the weight of the machine, and there it is here, and that's not taking the weight, so the impacts are weaker. This time waveform tells me about the nature of the fault condition and tells me about the severity. How many G's of vibration tell me how severe the problem is, and it's something that I can monitor over time. So that's a very useful sort of display. Here we have two gears, and if you look closely, they're moving closer together, further apart. Now it's all exaggerated, but if you look at this, it's eccentric. Could be misaligned, it could be bent. We see this pattern. But when we look at it as a time waveform, there it is. That's when they're closer together, and in between is when they're further apart. We get this pulsation of vibration. That's when the lower speed gear, it goes through the mesh, how the forces change, and that's the higher speed gear. You can see the little sort of pulsations in here. Now, the spectrum might show us this. These are sidebands in the spectrum. We didn't really explain that, but that's just one of the complications of, well, I shouldn't say it's a complication, it's actually very helpful, but we see all these little peaks, they're called sidebands. It means there's modulation. So if we do our spectrum analysis properly with enough resolution, we can see this. But we can see this for a lot of different reasons. When we look at the time waveform, it's telling me exactly what's going on. Here I'm showing looseness. There's the bearing sort of rattling around, or the shaft with the inner race. If you look closely, it's sort of rattling around because there's too much clearance, and maybe there's some unbalance driving that force, that motion. And here is the spectrum. I mentioned it earlier. We've got a lot of these peaks. That's the running speed, twice running speed, 3 times. These are harmonics. So sure, I would see that, and in this instance I'd probably think it was looseness. But when I can look at the time waveform, look at that. Bang, bang, bang. Each of those spikes is occurring once for every revolution of the shaft. So it's turning, going bang, bang, bang. Once per revolution, it's looseness. Like with everything in life, the more facts, the more information you have to help you make a decision, the better. Sure, I could just take a spectrum, and in this instance, I'd probably diagnose it correctly. But it is so reassuring to look at the time waveform and say, right, I know what's going on for sure. I know how severe it is. I know how quickly I need to act. And so when I say that some work needs to be done, my confidence level is much higher. I can make better decisions, and we can make decisions that could cost a lot of money if I get them right and save the maintenance work, or if I get it wrong and it fails. So the more information you have, the better, for sure. And here's the one we saw in the first place. What's actually happening is, as all of these good gear teeth are going through the mesh with the mating gear, we actually get this low amplitude vibration. See, in the gaps you see just low amplitude vibration, but when these 2 damaged teeth go through the mesh, boom, there they go through the mesh, big spike. There they go through it again. Once per revolution of this gear, we see a spike in the vibration. Now, often you'd be hard pressed to pick that up in the spectrum alone. It's a once per revolution vibration. There are other things you'll see in the spectrum, but the time waveform tells you perfectly, look exactly what's happening. And there are some cool ways that you can look at time waveforms. Well, I think it's pretty cool what we're seeing here, but you can mark it off in revolutions of the shaft. You can look at it wrapped around a circle and see that once per revolution it's occurring. All really cool techniques, but it's telling me exactly what's going on. By the way, we should do oil analysis as well, because the pieces of metal would go into the oil and we could detect that. So, very useful technique in parallel with vibration analysis with gearboxes. And that, you might wonder, what on earth is that? Now, you could get all cranky about it and say, oh goodness me, look at all those little spikes, what does it mean? There's not an even gap between them, gosh, I'm confused. Time waveform analysis is too hard. And that is a conclusion that a lot of people come to. The fact is, simplifying the story, if I look at a time waveform like that, then 2 seconds later I can move on to the next bit of data, because the time waveform isn't really telling me anything that I wouldn't be able to pick up out of the spectrum. The spectrum translates all of that into useful information. Assuming that we collected the time waveform correctly in the first place, I could look at that, and other than being interested maybe in the severity of it, how many G's of vibration we're seeing, that's all I'm really getting out of it. But this vibration is actually from this same gear, but in a healthier state. It just doesn't have the spikes. It's just the bit between the spikes, rescaled and everything. Anyway, that was time waveform analysis. There is another type of analysis we can do, which also adds information, and that's called phase analysis. Now, imagine, if you will, I'll come back to that. Oops, there we go. Imagine, if you will, that the machine is out of balance, and we can think about that shaft trying to move in a circular motion, and we can think about the vibration it would generate. But think about the machine itself. This is potentially a high-ish speed machine, whatever, just 2-pole, 4-pole, 6-pole motor. All that force translates into movement of the bearing. It moves up and down and side to side with, for example, unbalance. But it moves differently if it's misaligned, and it moves differently if there's cocked bearing and other sorts of faults. So that's what phase analysis does. Phase analysis lets us step back and think about what's actually happening to the machine as a whole. How is the vibration, or how's the fault condition causing the machine to move? And that tells us a lot about the fault. So, if we have a spectrum with a 1x peak and or 2x and or 3x, then there's a bunch of fault conditions that come to mind. It could be unbalance of varying types, misalignment, eccentricity, bent shaft, cocked bearing, etc., etc. You can see them there. From the spectrum, it isn't always obvious which of these faults it is. Now, if I was dealing with a fan and I knew that dirt sometimes builds up on the blades, dust, whatever product, and there was mostly 1x vibration, then I might be right in saying that it's unbalanced. That is the most likely. But do you know the most common reason why balance jobs fail? Because the machine wasn't out of balance in the first place. Someone sees high vibration, oops, that's unbalanced. Even if it's a high 1x peaks, it's unbalanced. And so the machine has to be stopped. A person gets in there, safety issues, all this sort of work, and then they find out, it's not out of balance, it's misaligned or something else. So, phase helps us understand that. Now, here is what we call single plane unbalance, static unbalance. The fan is very narrow compared to its diameter. All the unbalance is sort of concentrated, if you like, in one plane. And what's happening is, if you imagine a circular motion that we're looking at from the side, the two ends of the rotor, assuming it's supported at both ends, are moving up and down together. They are in phase. Instead, if we look at it on a bit of an angle, if we traced out, if you like, the orbit, or if we traced out the motion that bearing is going through in the way I'm animating it here, that motion would be circular. It wants to move in a circular motion because of the centrifugal forces of that out of balance weight. So, that tells us a lot. From here, if we could take a phase reading, we measure vibration here, and we measure vibration here, and we see whether it's going up together, down together, up together, down together. If we compared the vibration vertically here to horizontal, we would see that they're both going up and down, but there's a quarter of a rotation delay between the two. So if you look at it, it comes out to the side, then up to the top, then out the other side, then down the bottom, then this side, up the top, and so on. There's a phase timing relation. If we could compare the vibration vertically to the vibration horizontally, we would see 90 degrees phase change. 90 degrees because it's 90 degrees between vertical and horizontal, and it's moving in a circular motion. But you might think, well, wouldn't it always do that? No. With other fault conditions, misalignment for example, just about all of them, it doesn't move in a circular motion. It's very elliptical. It moves in funny ways you wouldn't expect. That's what phase tells you. How's it moving? So we come up with these little diagrams. We say, okay, the little circle and the line at the top is sort of like a reference. Rather than writing down the actual phase readings, we just draw it this way. So because the little line's going up in both cases, that means it's in phase. Because one's going at 12 o'clock and one's at 3 o'clock, that means there's a 90 degrees phase change, and it confirms unbalance. Here we've got, call it dynamic unbalance. The rotor's longer, the distribution of dirt buildup along the fan is not uniform, so therefore, if you like, it's more out of balance in one plane then another. Either way, that is still circular motion, but from one end to the other, it's not in phase like it was just before. So, looking over here, 12 o'clock, 3 o'clock, that's 90 degrees. By the way, it could be 12 o'clock and 9 o'clock, depends on the direction of rotation, but it's 90 degrees. But here, I've used 12 o'clock as the reference, and here we are at 5 o'clock. That shows that it's not the pure and simple in phase motion of static, and for what it's worth, it's not 180, which would be coupled. Phase really helps us to understand not only what's wrong with the machine, but in this instance, how to balance it. If I have an overhung rotor, not only do I get the circular motion that we just saw, but we also get a rocking motion. Let's have a look. So I'm not just showing the radial centripetal forces, I'm focusing on just the rocking. And once per revolution it sort of rocks back and forward, if you like, as that overhung rotor bends due to or flexes due to the out of balance on these blades. So it's still circular motion, so our 90-degree rule applies here and here, but we create axial vibration as well. So we measure that and we look at the phase reading. So this is, we put our sensor axially and see what happens. Now this all might be seeming just a little bit complicated. We're diving in the deep end a bit, but hey, look, 12 o'clock, 3 o'clock, 90 degrees. Now that is, what's that, 7 o'clock or something, and so there's 90 degrees between here and here as well. But notice that these ones are not in phase. But when I look axially, here compared to here, they are in phase. So bottom line is, phase really helps us understand what's going on. The challenge with phase is how you measure it. Now, the simplest way is to have a 2-channel analyzer, carry that second accelerometer with you, because you usually just take single channel measurements on a machine. And when you suspect a problem, you put, for example, one sensor on top, one sensor on the side, and say, what's the phase difference at the running speed between these two locations? And if it's somewhere around 90 degrees, aha! Now we take one sensor and put it in the axial direction, another sensor and put it in the axial direction here. And we say, what's the phase difference between these two locations at the running speed? They're pretty much in phase with each other. And so that's all you've got to do. If you don't have a 2-channel analyzer, then we have to use a timing reference. We often put a piece of reflective tape on the shaft and use a laser tack or photo tack to detect as it passes the detector once per revolution. That tells the analyzer the speed of the machine, and then it looks at the vibration from the sensor to look at the timing difference between that once per rev pulse and the sort of the height, the highest point in the time waveform. Anyway, bit of detail there, but it's a bit more complicated. You may even have to stop the machine to do the test. That's why a 2-channel analyzer is worth it. Okay, in this instance, we've got offset or parallel misalignment. Now, I'm simulating it. We've got the bolts undone, and it's free to move up and down. Maybe we're out in space. But of course, we're going to bolt the machine down, but the forces are still there. So if I put a sensor here and a sensor there, they are 180 degrees out of phase, whether I measure them both vertically or measure them both horizontally. With angular misalignment, not that you can see it, ignore that key, not that you can see it, but it's like pushes, pulls, pushes, pulls. We get axial vibration and we see a phase difference between this face and this face. We have to adjust them because we're pointing the sensors in opposite directions, but we will see that 180 degrees phase difference there. Eccentricity, it might look like unbalanced, but when we put the belt on and so on, we see something funny. A vibration reading taken in line with the belts compared to 90 degrees apart, perpendicular to it, those phase readings are often close to one another. They're sort of in phase, or they're sort of 180 degrees. When I say sort of, I mean we're not looking for 180.00, just something in that sort of area. It's because it's an elliptical motion, and we don't need to go into it all, but that's why we see that. And oh look, we've got the bearing isn't mounted correctly on the shaft. It's rocking and rolling every time the shaft turns, which is damaging our bearings. But if we compare the phase from here to here to here to here, we see a 90 degrees phase shift because of that rocking motion. Now, yes, we wouldn't take a reading here because we've got belt. I need to come up with a better illustration, but anyway, that's what we've got. Okay. On the other hand, if it's cocked in the housing, well, if I was to take a reading here and a reading here, in other words, on either side of the shaft, here compared to here, I would see 180 degrees phase difference, and I would see higher amplitude as compared to measuring here and on the other side. I might not see any phase relationship or any great amplitude. So with this type of problem, we're going to look at specific locations. Either way, it's either 180 degrees opposite if the bearing is cocked in that plane or in that plane. It's not 90 degrees as we move around. Anyway, I'm talking too much. Orbit analysis. Orbit analysis is intended for people who have machines with journal bearings, also known as sleeve bearings or plane bearings. Mostly for big critical bits of equipment like steam turbines, gas turbines, great big compressors, because then you can justify the measurement technique. So here is what's happening inside these machines. You've got the journal bearing itself. There's the bearing part with the special metal, and here's the shaft, or where it is inside the bearing, we call it the journal. So sitting underneath this is a wedge of oil that forms. So we pump the oil in, that keeps it supported, keeps it stable, keeps it cool, all sorts of good stuff. But unfortunately, if we've got some unbalance or whatever is causing the shaft to move, that vibration doesn't transmit well through the oil out to the bearing, and so therefore an accelerometer may not pick up what's going on. So we use these proximity probes instead. These two probes are sensitive to the distance between the tip and the shaft. So as it moves in this sort of direction, this one picks it up, moves in that direction, this one picks it up. The fact is we use it to triangulate. These two probes are mounted 90 degrees apart, and we kind of triangulate the motion of the center of the shaft. I'll explain that a bit more in a second. The third probe here is not in the same plane as these ones. This one might be at the end of the rotor or somewhere where there's a key or keyway, and it measures that displacement, and that gives us our once per revolution information. And one of the ways we would, what we'd like to be able to tell is just what is the rotor doing, what is the journal doing within that bearing. In this instance, we have oil whirl. This wedge of oil is actually following the shaft around as it moves in this big wide motion. It's using up all of the clearance that's available, hopefully still keeping that wedge there, but this is quite high vibration. It can't be any higher at this particular location. It can't be any more motion because it would start wearing away the bearing. But this is the sort of thing we'd like. We want to know in essence what the shaft is doing, what the center of the shaft is doing, because there are other faults in addition to unbalance and misalignment and preload and these sorts of faults. We're interested in the rotor dynamics as well, particularly as we go through the critical speeds. So in this instance, exaggerated, but that's the motion at the first critical, let's say. A lot of detail we could go into, but I'd be interested in how do I take measurements to tell that's what's going on. Well, imagine if we had our two proximity probes at 90 degrees apart, and they were taking the measurements, and we compared the two sine waves. We end up with a Lissajous figure, as it's often called, or an orbit. We plot the two sine waves against each other. We end up with a circle, if it is moving in a circular motion. And we plot that on a graph, as you can see here, y being the top, x being the side. There are so many details I'm leaving out, but just to give you a general idea, the orbit tells us what the center of the shaft is doing. So here we see this nice little orbit because it's moving in this small circular motion. More here, much more there, less and less, sort of similar. because that's what the shaft is doing, that's what the rotor is doing. Now we may not be able to put proximity probes in all these locations. I'm just showing this for illustrative purposes, but this is the orbit, and that orbit tells us, it may be small and circular, that's good. It may be bigger and elliptical, and then we have to start to ask, well, is that okay? Could it mean there's some preload or misalignment? If it gets big, then it could be the oil whirl we just looked at, or oil whip. So there's lots of things we could talk about with all these topics, but what I'd like to do is just summarize what I think are some of the more important points. So spectrum analysis is the most commonly used vibration analysis tool. The peaks that you see normally relate to the components within the machine: the shaft, the vanes in the pump, the bearings, and so on. What we do is we take routine measurements according to the PF interval, or the rate of failure, and we look for changes in amplitude. We look for new peaks that are appearing, we look for sidebands and harmonics, and generally we are looking at the pattern to try and tell what's going on and how severe it is and how quickly it's changing, which tells us how quickly we need to take that maintenance action. So we therefore try to assess the condition from the pattern and the severity from the amplitude, basically. But the waveform and phase, time waveform and phase, gives us additional information, as do other condition monitoring technologies. Vibration's a condition monitoring technology. Oil analysis, wear particle analysis, infrared, ultrasound, motor current testing are all routinely checking the condition of the machine. Now, time waveforms show us what happened from moment to moment. It's like taking that movie and analyzing every frame of that movie. Okay, as the gears mesh together, is it going well? As the balls roll around, is it going well? It gives us that detail. Not enough people use this tool. I've heard all kinds of excuses, and I don't mean to offend you if you're not doing it. Bottom line is, it's not hard to measure it correctly, and if you do measure it correctly, it's a lot easier to analyze the data. It shouldn't take you that much longer, but when it helps you, boy, what a bonus that you've got that information. Now, phase, on the other hand, helps us to understand the motion of the machine. That tells us about everything from unbalance to misalignment, looseness, resonance, all sorts of fault conditions that can be picked up thanks to phase. And we may even see, or we often do see, changes in the spectrum, but making sure that we've correlated correctly what those changes are to what the fault condition is, potentially means the machine failing or not, or getting unnecessary work done, that sort of thing. And my last comment, I made the comment at the very beginning, but I'd just like to repeat it. Some people use vibration analysis almost like a troubleshooting tool. We're taking measurements just like old Joe used to with his screwdriver, and just like an operator might hear that the machine has a problem. We are hearing and detecting problems that shouldn't exist, and we are just often looking for the bearing faults, the thing that we think, oh well, that's what's going to cause the machine to fail, so let's focus our attention on detecting bearing faults. All of that is good. All of that justifies the training and the equipment. All of that is important, but you can do so much more, because if we detect those root causes like unbalanced misalignment, lubrication problems and soft foot and so on, if we detect those early and correct them, then the bearings probably won't fail. And we, depending on your industry, we might improve quality, we may reduce energy consumption and all those things if we eliminate those root causes. But whereas vibration can be used to detect the root causes, we can go even a step further and say, let's use vibration to try and prevent the root causes. Let's be proactive. Let's put a force field around the plant and use vibration analysis for acceptance testing. Let's test that pump and the motor and the fan as it comes into the plant in agreement with the vendor, and we tell the vendor, if it doesn't pass our vibration test, we're not accepting it. Now you might think, why would you do that? Of course the brand new pump or the recently rewound motor they're going to be in great condition, aren't they? Not always. And as soon as you accept that equipment, boom, it's your problem. And the problem may not appear for a few months, and then there's a, well, you caused it, you did it to the machine, the way you operated it, the way you installed it. No, this has got to end. You want the design and procurement process to be done with a priority given to maintainability and reliability and operability, and then we use acceptance testing to make sure that everything that comes into the plant is good. We detect the root causes, and we use vibration also as a sort of a QA, quality assurance, quality control process, so when work is done on a machine, we test to make sure that the work was done properly, up to our standards. So, thank you very much for sitting through this hour-long presentation. I hope you've learned a lot. I hope it's been worth your time. I've tried to summarize all the technology so that you can see where they should be used, which one gives you what piece of information. I hope you found it useful. We run lots of vibration courses on this topic all over the world. Basic training category 1, 2, 3, and very advanced training category 4. All with our animations and our simulations and all the rest of it. We also have distance learning if you don't want to go to a class. We have e-learning as well, I Learn Vibration. We even have Interpreter that actually helps you analyze the spectra and tell you what's going on. But you'll also find lots of free stuff on our website. If you go to mobiusinstitute.com, go to the Knowledge Center, you'll find lots of little videos just like this one, lots and lots and lots, that tell you about all sorts of topics. But as of this recording, we haven't yet released the 9 minutes of knowledge presentations. You can see that when I get talking about these things, we're up to 56 minutes. 56 minutes. It's a long time, and you may struggle normally to set aside that much time. So what we've done is created a whole lot of mini presentations on topics, and the presentations take 9 minutes or less. So you can just say, great, I want to learn about soft foot, or root cause failure analysis, or vibration analysis, spectrum analysis, time waveform analysis, whatever. So you'll see those coming out soon. If you're not on our mailing list, please get on it. Email this address or visit this website. Thank you very much for viewing this presentation. I do hope you found it useful. Please fire any questions into us. We'd be glad to help you. Thanks a lot. Bye.